Good day, class. Today, let's discuss the relative motion in one dimension and two dimensions. Take note again of these four kinematic equations as they are very essential in our problem solving. Usually, a moving body is observed by an observer who is at rest. Commonly, the position of the observer is denoted as the reference or fixed reference. This fixed reference is what we call absolute or Newtonian or inertial frame of reference. For most of the moving bodies, the Earth is regarded as the fixed reference, although the Earth itself is moving. In fact, the Earth is rotating around its axis and is also revolving around the Sun. For the different types of motion that we have covered so far, we considered any reference to be a fixed reference when it is at rest on the ground or is not moving relative to the Earth. Motion referred with such reference is what we call absolute motion. In fact, all our previous lectures are under absolute motion. Now, how about if the observer or the reference itself is moving? For such motion, we refer to that as relative motion. A simple example is this one in where an observer, let's say the one inside the hot air balloon, is actually moving aside from the motion of what is observed below. To get a better grasp about relative motion, let's discuss this simple case example. As you can see in the figure, we have two racing cars moving with different speed along a straight track. Let's denote the white car as car A and the blue-green car as car B. Let's assume that car A and B are moving with a speed of 60 and 80 kph respectively. These two values of speed are based on absolute or fixed reference, and therefore they are considered as absolute speeds. This means that for any static observer, these values of speed are what they can measure from these racing cars. Based on this case example, you can observe that car A is slower than car B, which means that if you're riding the car B, you will perceive the car A to be moving backward by 20 kph. Similarly, if you're riding the car A, you will perceive car B to be moving forward at a rate of 20 kph. But you might wonder, with these relative observations, where did this value 20 kph come from? To answer that, let us look now at the necessary formulas that you can use to deal with relative motion. Let us now consider this figure as our basis for the formulas in one dimension. As you can see here, we have two particles denoted by A and B moving along a straight path, and our reference point is at point O. As particle A moves, we can represent its position as x sub A. In the same way, for particle B, we can denote its position by x sub B. From these positions, we can find the position of particle B relative to particle A by just getting the difference between x sub B and x sub A, and we can represent that as x sub B over A. Notice that in the subscript, B is above A, which means that the observed particle is placed in the numerator while the observer is placed in the denominator. Based on this diagram, we can now have the equation for relative position, which is just the difference between the two positions. One way to easily remember this equation is to follow the pattern in the subscript. We can express the relative position equal to the position of the particle indicated as numerator in the subscript minus the position of the particle indicated as denominator in the subscript. Thus, relative position of particle A with respect to B can be expressed as follows. If we differentiate these two equations with respect to time, we will now have the equations for relative velocity. Notice that the pattern of their subscripts is still the same with the previous equations. When we continue to differentiate these two equations with respect to time, we will now have the equations for relative acceleration. Even here, the pattern of the subscripts still applies. Let us now proceed with the sample problems about relative motion. For problem 1, we have here a scenario of a boat race. Boat A is leading boat B by 50 meters and both boats are traveling at a constant speed of 180 kph. At t is equal to 0 seconds, the boats accelerate at constant rates. Knowing that when B passes A, t is equal to 8 seconds and v sub A is equal to 225 kph. So determine the acceleration of A, the acceleration of boat B, and the relative velocity of boat A with respect to boat B in meters per second. So for this problem, as you can notice, we can only apply the concept of relative motion in the last requirement. However, in order to solve relative motion, you must have a solid background about rectilinear motion and in other cases, projectile and curvilinear motion. So for this problem, we will set the reference at t is equal to 0 seconds in the case or in the scenario in where both B and both A are 50 meters apart. And we will set all vectors directed with the same direction as positive. So we are given here the initial position of boat A equal to positive 50 meters, the initial velocities of the boats when time is equal to 0 seconds, that is equal to positive 180 kph, and the final velocity of boat A equal to positive 225 kph. So take note that this velocity or this final velocity of boat A will be the value of its velocity when boat B is able to catch up with boat A. And the time that boat B will be able to catch up must be equal to 8 seconds. So the required is A sub A sub B, and V sub A over B. Okay. For our solution, let's start with A sub A. So before we dive into using the rectilinear formulas, we must convert first the values of velocities from kph into meters per second. So converting the values of velocities, the converted value of initial velocities of the two boats is equal to positive 50 meters per second, while the final velocity of boat A is equal to positive 62.5 meters per second. Now, to solve for the value of A sub A, we must use the second kinematic equation, and by substituting the available values, we can observe that from this equation, we have only one unknown, which is A sub A. Therefore, we will be able to solve A sub A, and that is equal to positive 1.563 meters per second squared. So this is the answer for the first requirement. So next, let us now solve the value of acceleration of boat B. Let's take note the known values including the obtained value of acceleration of boat A. In order to solve for the acceleration of boat B, we must consider the situation in where boat B is able to catch up with boat A at time equal to 8 seconds. This means that by using our reference, the final position of both B and both A must be equal. So this equation will prove to be useful by the time that we relate the motion of the two different bodies. So first, let's start by analyzing the motion of boat A. So we will use this third kinematic equation in order to obtain the final position of boat A. So after obtaining x sub A, we will use of this equation in order to get the value of x sub B, which is just equal to x sub A, and then we will proceed to analyze the motion of boat B. So by substitution of known values, we'll be able to get the value of x sub a, which is equal to positive 500 meters. So by using this equation that relates these two different bodies, we can conclude that x sub b is just equal to positive 500 meters. So now let's proceed with the motion of both b. So by using again the third kinematic equation, we'll be able to get the value of a sub b, which is the unknown or the requirement for this problem. So by substitution of known values, we can observe that the only unknown variable is a sub b. Therefore, we can find the value of a sub b, which is just equal to positive 3.125 meters per second squared. Lastly, we are required to solve for the relative velocity of both a with respect to both b. First, let's take note of the known values, including the obtained value for a sub b or acceleration of both b. Since we are required to solve for the relative velocity, we have to take note that for this problem, the observer is on both b and then the observed body is both a. If you can recall, we can simply write the equation for v sub a over b by following the pattern of the subscript, and that is equal to v sub a minus v sub b. Since v sub a is the value of v sub a is already known, we need to find first the value of v sub b. So by using this second kinematic equation to solve for v sub b, we need to substitute the known values, and that is 50 for the initial velocity of both b, and 3.125 for a sub b, and 8 for the time. This will give us the value of v sub b equal to positive 75 meters per second. Now that we have the value of v sub b and v sub a, we just plug in these two values in this equation to solve for the relative velocity. So by substituting the value of these two absolute velocities, v sub a and v sub b, we need to consider also the sign. So for example, if one of them is negative, we must substitute, for example, v sub a is equal to negative 62.5. We must also include that negative sign in this equation. So for this problem, our relative velocity is equal to negative 12.5 meters per second. So the meaning of this negative sign is that it indicates that if you are riding boat B, you will perceive boat A to be moving backward with the magnitude of 12.5 meters per second. So this happens because boat B at time is equal to 8 seconds has a greater velocity compared to boat A. So the observer on boat B will perceive boat A as if it is moving backward, where in reality, based on absolute reference, boat A is actually moving forward. Let us now proceed with our second sample problem. In an elevator shaft, a ball is thrown vertically upward with an initial velocity of 18 meters per second from a height of 12 meters above the ground. At the same instant, an open platform elevator passes the 5-meter level, moving upward with a constant velocity of 2 meters per second. So for this problem, let's denote that all vectors directed upward are positive, and let's write the given initial position for the ball and the elevator, and also the initial velocity of the ball and the constant velocity of the elevator. So we are required first to solve when and where the ball hits the elevator and the relative velocity of the ball with respect to the elevator when the ball hits the elevator. To start our solution, let us also include the implied given values, including the acceleration of the ball, which is equal to acceleration due to gravity, and the acceleration of the elevator, which is just equal to 0 because of its constant velocity. To solve now for the time and the position of the collision of the ball and the elevator, let's make use again of this drawing. As two bodies move upward, there is actually two possibilities of their collision. And this one is one of the possibilities of their collision. The other possibility is when the ball moves upward, reaches its maximum height, and collide with the elevator on its way downward. So the question now is, which of the two should we consider in our analysis? So to avoid such complication, what we will do here is we will consider only the final positions of the ball and the elevator. So whatever path they will take, their final position must be equal with respect to the reference. Later on, this will serve as a way to relate the two different motions. Let's start the analysis with the motion of the ball. So to determine the final position of the ball, we will use the third kinematic equation, and by substitution of the known values, we will express the final position of the ball in terms of variable t. And we will set this equation as our first equation. Next, we will proceed with the motion of the elevator, and this time we will use the first kinematic equation because the elevator is under the uniform rectilinear motion, or a motion with constant velocity. So by substitution of known values, we will also get the equation of final position of the elevator in terms of variable t. And we will set this as our second equation. Since the final position of the ball and the elevator are just equal, then we will just equate equation 1 and 2, and this will give us this quadratic equation. Solving for the value of t using the quadratic formula, this will give us two values of time. So the one is a negative value, which is absurd because there is no such thing as negative time, and the other one is a positive value, which is the final answer for this question. So this means that at this time, the ball and the elevator collided. To get now the final position, we will just plug in this value to our second equation, and this will give us the position of their collision, which is equal to positive 12.31 meters. Lastly, we are required to solve for the relative velocity of the ball with respect to the elevator. So for this requirement, take note that the observer is on the elevator and that the observed body is the ball. So we know that the needed formula for this requirement is, or can easily be determined by following the pattern of the subscript. So we just need the velocity of the elevator and the velocity of the ball. So the velocity of the elevator is just a constant value of positive 2 meters per second. So we need now to determine the velocity of the ball upon collision. So at this time of collision, the velocity of the elevator is just a constant value of positive 2 meters per second. And for the velocity of the ball, we will use the second kinematic equation. So by substitution of the known values, including the acceleration due to gravity, so we will get that the velocity of the ball is equal to negative 17.84 meters per second. So take note that these two velocities, v sub b and v sub e, are absolute velocities. So the negative sign for the velocity of the ball indicates that the ball is already moving downward when it collides with the elevator. So the governing case now for the collision of the two bodies is the one that is drawn in dashed line. So the ball is already moving downward when it collided with when it collides with the elevator. Now that we have the values of v sub e and v sub b, we can now compute the value of the relative velocity. So velocity of the ball is negative 17.84 minus the velocity of the elevator, that is positive 2. So this will give us negative 19.84 meters per second. So the negative sign means that if you are on the elevator, it will appear that the ball is moving downward, and when it comes to the magnitude, so 19.84 meters per second is greater than the magnitude of the absolute speed of the ball, or the absolute velocity of the ball. So the magnitude of the absolute velocity of the ball is 17.84. So that means that for an observer, he will perceive that the ball is moving at a speed greater than 17.84 meters per second. So that happens because both bodies are moving towards each other. Therefore, the observer will perceive the ball to be moving at a speed faster than the actual speed.